In the previous video, we studied the concept of compound interest, with the idea that if money is invested in an account that earns a certain percentage interest per year, and we compound that interest um, at set intervals, then of course we're going to earn money um, on top of what we invested. And the same goes if you're thinking of it as a loan, right? So if you take out a loan for a certain amount, then you are going to have to owe interest on what you borrowed. And we had a formula for when we compounded, say, quarterly or monthly or annually. And we worked with that formula to answer questions about how much money's left in an account after, so many years, or how much do I need to invest in order to have a certain amount of money in my account after, 5 years or something like that. So, with this idea that we can compound our interest at different intervals, we might wonder, well, what if we're just always compounding our interest? So, this brings us to the idea of continuously compounding interest, right? So, in general, it is better to compound your interest more often because you can earn interest on top of the interest throughout the year. So, if you compound the interest continuously, then what does that exactly mean? Well, the formula for how much is in the account after a certain amount of time is going to be completely different than the compound interest formula that we used before when we were compounding n times per year. So we're going to have one that looks like this. And it's really interesting because if you look back at the compound interest formula in our previous video, the R, the percentage rate, um, appears not up in the exponent, but down in the base. Whereas with continuously compounding interest, it appears up in the exponent. Now, to really explain why this is, we need to do just a little bit of light calculus. So I'm not going to go through that in this video. Although, if you are interested in how we arrive at this equation, definitely, shoot me a message. I'd be happy to share some more detail with you. But if we see continuously, then this is going to apply to things like inflation, right? So the concept of inflation, where how much buying power your money has, just does change over time, and that's kind of something that is happening more or less continuously. It's just kind of happening all the time, as opposed to like every 3 months, all of a sudden, um, the amount that you can buy with a certain amount of money changes. So this first example. So suppose the inflation rate for continuous compounding is 3%. If it costs a family an average of $48,000 per year to live in 2010, how much will it cost to live in the year 2025 and 2050? All right, so with this formula here, we have amount equals the principal. Okay, well, 48,000, right, is kind of that starting amount that we have. E to the, and my R is 0.03. That's my continuously compounding percentage growth rate. And then to the T. So there's my formula. So it's saying in 2010, so what we're going to say is that T equals 0 is 2010. We're kind of thinking of that as our starting place. So it says in 2025, how much uh, will it cost to have kind of the same standard of living that 48,000 bought you in 2010? Well, 48,000 e to the 0.03, and in 2025, of course, 15 years have gone by. All right, so we'll go ahead and put a 15 in the exponent. And when I go ahead and make that calculation, okay, then I end up with $75,278.98. Okay. So if you have an inflation rate of about 3% per year over a 15-year period, then you can see that, if you're getting paid 48,000 a year, just to keep up, right, with your same standard of living, your salary is going to need to grow all the way to 75,000 15 years later. And it's even more drastic when you pick a number like 2050. So that's 40 years later. So we have 48,000 e to the 0.03 times 40. And let's remember that we have talked about this number E in the past, right? E is, approximately 2.72. It's an irrational number. It's like the number pi. So it's probably worth just talking a little bit about typing something like this in your calculator. So if we happen to be using Desmos, then uh, if you just type the letter E in here, it knows what you're talking about, which is kind of nice. So you can just type it straight from the keyboard if you'd like. Um, you can also, go through the menu here, and here's e to the x. Okay, so it'll do e with an exponent in there for you automatically. All right, so if I'm typing this in, 48,000 e raised to 0.03 times 40. What I would just say here is that if you are doing this in a handheld calculator, then depending upon how easy it is to type in everything at once, you might want to do the 0.03 times 40 first, then take e raised to that number, and then multiply by 48,000. But as you can see, we get a pretty big number here. So we end up with $159,365.61. Now, if you think about starting, your uh, starting a career at say age 25, 40 years later, that would be age 65. So that's about when you want to retire. So if this is what you were making when you were 25, then this is how much you'll be spending to maintain that same standard of living when you finally do retire. So it's important to be putting money away for retirement, because you are going to have even more money available essentially um, than you might think. Now, of course, inflation isn't always 3%. A lot of times it's lower. Of course, lately it's been higher. So, over time it can kind of even out. It might not be quite as high as 3%, but this just gives you an idea of the types of things you need to think about. All right. Now we have an insurance broker deposits $2,500 into an account which earns 8% annual interest compounded continuously, right? So there's that key word. It's compounded continuously. The moment I see that, rather than writing down the formula we used in the previous video, I'm writing down this one. Um, so it says, in approximately how many years will the investment be worth $7,500? Right. Well, first of all, we invested $2,500, right? So that's definitely our principal. We know that R has to be 0.08. They're saying we want it to be worth 7,500 bucks. So that means we know the amount needs to be 7,500 bucks. And so, of course, what they're asking for is in how many years? So the question is, what is T, right? All right. But um, if we look at what we've got going on here, this is actually something we do know how to solve, although it looks a little worse than maybe we saw it in the past. So let me just over on the side in a different color here, just over in red. I'm going to do just a different problem. Okay. This is one that you have worked on previously. So suppose I have 2e to the 3t minus 5 is equal to 7. All right. We have worked on solving this. Remember, what we would say is that we have an exponential that we want to solve for something up in the exponent. So we need to get the exponential by itself first. We, of course, would divide by 2 on both sides. So e to the 3t is equal to 6. And then remember here, we would realize that if I took the natural log of both sides, it would just give me 3t on the left and the natural log of 6 on the right. So then the last thing would just be divide by 3. So t, and I'm running out of space, but I think I have just enough, equals the natural log of 6 over 3. Okay, so we know how to do that. We've worked on that before. Here, this is the same thing. It's just the numbers aren't quite as nice. So I look at this and I see, you know what? I need to get the exponential by itself. So let's divide by 2,500 on both sides. So on the left side, we end up with 3. Right side, e to the 0.08t. Take the natural log of 3. Take the natural log of the other side. So we have the natural log of 3 is equal to 0.08t, right? The whole idea of the natural log and the e kind of eliminating each other. And then finally divide by 0.08. And the natural log of 3 divided by 0.08, that's something that I can get an approximation for. So I have t, and then when I punch that in my calculator, I get about 13.7 years, right? So if I want to, essentially in this case, we're tripling, right? If I want to triple my investment at earning 8% interest compounded continuously, then I need to invest it for about 13.7 years. So one more example with continuously compounded interest. It says Hector invests $10,000 at age 21. He hopes the investments will be worth 150,000 when he turns 50 years old. So he's planning for the future here. If the interest compounds continuously, approximately what rate of growth will he need to achieve this goal? Okay, so again, we see continuously. So we write down A equals PE to the RT. So he wants it to be 150,000, right? So there's my A. He's investing 10,000. So there's my P. E to the, now it's asking me what rate of growth, right? So that's my R. They do tell me T, right? Because they're saying at age 21 and then when he turns 50. So the span between 21 and 50 is 29 years. So we're going to plug in R as a letter, but then 29 as the T, right? So 50 minus 21. But I just have one unknown. So like in that last problem, my first task is to get the exponential by itself. So we'll divide by 10,000 on both sides. And quite a bit of simplifying you can do here because, and if both numbers end in zeros, you can just cross off the same number of zeros in both numbers. So you end up with 15 is equal to e to the, and it's always kind of convention to put the number first and the variable second. So e to the 29r. So we'll take the natural log of 15 and the natural log of e to the 29r. So our last step here is just to go ahead and divide by 29 on both sides. So that gives me approximately 0.093. So 9.3% would be the growth rate you need, which would be a really good growth rate. It would be quite a good one for sure. But also not so far out the realm of possibility that it's completely impossible. So you can see planning ahead Hector can do pretty well for himself over that 29-year span.